Okay. Hello everyone. Good afternoon. It's 12:10 and times to start our today's Astroph. Today we have three presenters: Vignesh, Shuri, and me. Who is volunteer to go first? Okay, Vignesh.
Okay, let me share the screen. Just a moment. Yes. So, is my screen visible?
Yes, yes.
Okay, good. So, yes. Hello, everyone. I would like to present this paper where they calculate a component called as real and the pseudo dispersion measure of this particular FRB. So we all know that as FRB propagates through the interstellar medium, it interacts with the free electron, and this interaction results in a dispersion measure. And this dispersion measure is often used in different aspects in the FRB science. Especially, it is used as a distance indicator to do cosmology, to identify the whole redshift of the FRB, so on. So, however, the authors claim that the dispersion measure that they calculate has a little bit uncertainty than the true dispersion measure. So when they so this dispersion measure result, which is resulting from the interaction between free electron, they call it as the dispersion measure real, so dm real component. However, in practice what we usually do is we fit a model to the profile and obtain the dispersion measure from that particular model, and this is called as this dm model in this, according to this paper. So what authors they are claiming is that this dm model is little bit far from the true dispersion measure caused by the interaction of free electrons with ism. So this discrepancy is often related to the intrinsic burst morphology. So if the intrinsic burst morphology of the FRB changes, that could result in slighter different DM values, which is often calculated when we prefer the DM calculated from the model value. So this apparent change in the dispersion measure is called as the pseudo dispersion measure, according to the paper. So what they are saying is that for this particular FRB, in order to calculate the whether the pseudo dispersion measure and the real dispersion measure are very pretty much closer or very far, what they do is they assume two things. One is that for any FRB in general, if they wanted to do these kind of analysis, it should be presented in a non-magneto ionic environment. In other words, so since they are talking about this particular FRB, they are saying that this particular FRB should present in a non-magneto ionic environment. And also the DM variation, often in repeaters we can see a slighter DM variation when we observe it for longer duration. So what they are saying is that the DM real, which is the true DM variation, should be smaller than 10 power minus 2 parsec per centimeter cube over a few years. This is the first assumption. And the second assumption, what they are doing is that they are taking micro shots. Micro shots are nothing but it is a high definition images. So basically, if you take a normal pulse profile, the x-axis would be in the order of x-axis would be in milliseconds to seconds. But in micro shots, what we do is we go very detailed high definition images. So we take the images in scale of microseconds, so several tens of microseconds. So this is called as micro shot. So what the second assumption what they are taking is, even though within a single micro shot of a particular FRB, there will be some burst morphology variation, and this variation, the time delay caused by this variation, should not be non-negligible quantity, should be a negligible one. So these are the two assumptions that they are taking in order in this paper. So by using these two assumptions, what they did is they found two other micro shots for this particular FRB. Actually, in previous literature, there are some studies regarding this microshots of this particular FRB, where the authors of that particular paper, they found two microshots, and here newly they are finding two other microshots, and combining this, they are taking four microshots of this particular FRB for the to get the DM real contribution and to do the comparison. So yes, I'll move on to the equation. Yeah. So theoretically, you can see that if the intrinsic morphology changes, then it affects the real quantity of the dispersion measure. You can see according to this equation, the change in the delay time. I mean, the change in the time scale which is caused by the intrinsic morphology changes will affect the real dispersion measure that we are obtaining for a particular given frequency range. So I'll go to the image now. So figure one shows the two new microshots that have been identified for this particular FRB. So the here they are giving an interesting approach to calculate the dispersion measure. So how do they do it is that for each part of the profile, so for each part of this profile, they take a small sample from, let's say they take this small sample between this point and this point, and what they do is they try to guess the initial dispersion measure values, and they try to change different dispersion measure values, and try to see how the signal to noise ratio changes. In other words, once we do that analysis, we get a uh, distribution where the dispersion measure as a function of signal to noise ratio. That is the figure shown in the bottom panel. And once they fit a Gaussian profile with a constant, I think it's Gaussian profile with a constant baseline. I don't know why how they fit this for this particular FRB, but apparently the fit, I don't know how strong is the fit here. But after fitting a constant Gaussian profile with a constant baseline, they get a best parameter, that is the dispersion measure for this particular microshot. And they do the same analysis for different microshots. So once we get the dispersion measure, it's time we compare it to the with the dispersion measure that is obtained from the model calculation. So that is given in the figure 3. So figure 2. So you can see that this figure shows the evolution of dispersion measure that is taken on different observation period, basically on different days. So here what they are doing is they are comparing this micro shots, that is the green markers of the particular FRB, with a narrow burst that has been studied for the same FRB but in a different paper by Zhang et al. So in Zhang et al. 2023, they study 9 narrow bursts of this particular repeating FRB, and they obtain dispersion measure value. So when they compare it with, and this red dotted line shows the mean dispersion measure that is obtained using this micro shots. So you can see that, and this gray color is the DM fitted one, the model one. You can see that the comparison, when we compare the uncertainty range of fitted model versus the DM that we got from the microshot and the narrow bus, you can see there is a huge discrepancy between these two quantities. So what they are saying is that, so in order to use the dispersion measure, in order to calculate dispersion measure, using microshots method or using narrow burst method is more relevant, I mean more accurate compared to using the models. So yes, that's the major discussion from this point. So here what they are doing is that they are trying to compare it with different repeater FRBs, and the dispersion DM, this black color curve corresponds to the DM model that is calculated using the model fit data. And yes, when they try to compare it with the different other repeating FRBs, most of the case they see a positive separation between the true dispersion measure and the model calculated value. And this separation is not due to the change in the local environment, rather it is due to the intrinsic burst morphology changes of the particular repeater FRB. So yes, that's all from me. So yeah, in conclusion, what they are trying to say is that they figured out that in order to get a good accurate value of dispersion measure, we can use either microshots method or the narrow burst method mentioned in Zhang et al paper, rather than just relying it on a model. If we are trying to consider a model, then we need to consider for the fact that there is a apparent change in the true dispersion measure calculated by the model and the this method. So yeah, that's all from me.
So thanks, beginners. So when you correct for the model, for the single FRB,
Mm-hmm.
how do you correct for using this model? And then how accurate is this correction? If I look at your figure, actually this suit the dispersion measure is not so large, right? It's just
Like
point one or two.
point 5 plus minus point 0.5 maximum. The apparent uncertainty range is plus minus point 0.5.
Okay, so my question is for a single burst, how do you use correct for this using that the model you mentioned?
For single burst, I am not sure about that, professor. Like, I have
Eh,
to check that.
Didn't you say that you can correct using a model? No?
No, no, I didn't say I can. They compared it with the model. I didn't say like they correct using the model. They just showed
Okay.
that when they compare it with the model calculation, there's apparently change. Someone, I think yes.
Uh, Vignesh, I have maybe follow-up question
Yes,
related to
professor.
Thomason's point. Say, if we look at this figure,
Mm-hmm, mm-hmm.
so this daily DM distribution is actually overestimating DM
Mm,
compared to
mm,
narrow
mm,
micro shot.
mm, mm, mm,
But then I wonder if this overestimate is only for this particular case. Say, if
mm.
just like what Thomason mentioned, say we are detecting many different FRBs,
Mm,
right? And
mm,
then if depending on intrinsic morphology, this
mm,
can be underestimate. I'm not
mm.
sure. If it is
No,
changed for different FRBs, then maybe
uh,
difficult to correct for that.
maybe can I answer it here? So
Sure, sure,
what
sure.
they are saying is that not here. Somewhere, yeah, this guy. So what they are saying is that this apparent shift between the model and the this calculation, narrow burst calculation,
Hmm.
for other repeaters, it is always that the difference is in positive region. Like, so basically the model is
So
trying to overfit.
why?
They, I don't know why, but they are saying it somewhere in this paragraph. uh, for each source, alpha is sources it a substantial. I don't know why, but they are saying that mm, they try to figure out whether this apparent change is caused by the sudden environmental change around the FRB location, or due to the burst morphology. So
Hmm.
when they try to check these two, try to understand these two origins, they are saying that it is highly unlikely that this change can be caused by the um, our change in the magneto-ionic environment, rather than the burst morphology. So they are saying that burst morphology might be the main reason for this apparent overfitting.
Hmm.
So that is what they are saying, I guess.
I see, I see.
Uh, okay, is there any, thank you, Vignesh. Is there any other questions or comments to Vignesh? If no, we can move on to our next presenter.
Thank you.
I can go first. Okay, let me share my screen. Okay, today I want to talk about this paper that uses JWST mid infrared data to measure how dusty star-forming galaxies and aging evolve from redshift 0.5 to redshift 6. And they show that JWST can detect faint dusty galaxy populations better than previous works. And this is important because a large fraction of a star formation and black hole growth is hidden by dust. And so optical and UV data miss it. So mid-infrared light traces dust emission, and it's essential for measuring the obscure universe. And the main primary goal of this work is to first calculation of monochromatic mid-infrared luminosity function, and then they calculate total infrared luminosity function, and then using they calculate AGN luminosity function, and by that they find the history of dust obscured cosmic star formation and black hole accretion density history. And the data they have used is JWST SMILES, which contain 8 millibands from um, 5.6 to 25.5 micron, and they matched their data with JADES, both optical and near infrared photometry. And by this, they have 2,830 sources, and after some quality cuts, it was around, I think, 2,060, 607 sources, reliable sources remain for analysis, and they here is the number density of number of sources by their magnitude, and the method that they have used, they use easy photometric redshift and compare it with a spectroscopic redshift that were available for that sources. And they found that using only near infrared data disband have a better photometric redshift than using near infrared plus mid infrared. So they adopt only near infrared redshifts. And for STD fitting, they use SIGAL and to fit galaxy STDs and estimate physical properties of the galaxies, and they want to know that whether their galaxy contain a significant aging component or not. And for for selecting the sample, they use frag agent, which is a parameter of SIGAL, and simply is luminosity of AGN divided by luminosity of AGN plus luminosity of galaxy. And they select and adopt their AGN, their samples that have more than 20% hosted by AGN. So if this fraction was greater than 0.2, they assume that it's AGN host, and by that they find 534 galaxies, which by using this criteria was AGN hosts, and which this 534 AGN was 90% of their total galaxies that they have. And they started to computing luminosity function, and here, yes, here in figure 8 to I think figure 50, they plot their luminosity function of different bands. For example, this is for 5.6 micron. These are monochromatic luminosity function, and they try to match it with, they compare it with previous works, and we can see that their work gain a fainter end, and at the brighter end, they are matched with previous data. These are just a luminosity function of each band, and here, yes, here is total infrared luminosity function in every band. They use this vertical line is the completeness. They adopt completeness of more than 80%, and they don't include these data were incomplete in their fitting. And it's they also compare with previous data, and using their fit, they can calculate the faint end slope, and we can see that at higher redshift bin, the slope is too much steeper, and around this redshift bin is flattened and shallower. And also for that 534 AGN host galaxies, they also calculate and they also plot the luminosity function and try to try to calculate the best fit and compare with previous works. We can see that trend is remain at higher redshift. The slope is steeper, and at this redshift is shallower and flat. And using that luminosity function and integrating over integrating using this formula, they can find a density of AGN and density of galaxies that they have. And this plot is just best fit for different redshift bin. As I said, we can see that it's at higher redshift, it's the slope is steeper, and at lower redshift is shallow. And by that formula that I've mentioned, they calculate the density, luminosity density of infrared across redshift. We can see that at cosmic noon around redshift 1 to 3, it has a peak, which is reasonable because we know that here Cosmos is more active, and they create more galaxies, and galaxies contain more dust. And for AGN, they have also used the luminosity density, and which is in this figure. We can see that for redshift lower than 3, it's completely agree with previous works, but for higher redshift, it's a little bit higher, and they've mentioned that it's because of the thing that maybe there are some AGN which are hidden by X-ray surveys before, and they were more um, obscure AGN in early universe, and more faint dusty galaxies may be there. Yes, that's all from me. It's the summary of this paper. Uh, any questions or comments to me? Okay, if not, we can move on to our next presenters, Shuri.
Okay, let me share my screen.
Okay.
So I will be discussing this paper, the Massive and Distant Cluster of Ice Survey 2, Detection of Splashback Radii in Galaxy Cluster Total Light Stack. So this paper, it focuses on understanding the true physical boundary of galaxy clusters using a feature known as splashback radius. To begin with, the galaxy clusters, they are not isolated systems. They are constantly growing by accreting matter from their surrounding. And as galaxies and dark matter fall into this cluster, they don't simply stop at the center. Instead, they move through the cluster's gravitational potential and orbit within it. So this splashback radius, it corresponds to a location where this infalling material reaches its first outmost point, also called as the apocenter, after falling into their halo. And because of this, it marks as a natural physical boundary between matter that is already part of the cluster and matter that is still falling into the cluster. So observationally, this boundary, it appears as a sharp drop in the density profile, or in their work, the light profile of the cluster, it decreases. The authors say that traditionally this splashback radii, it has been measured using galaxy number counts or weak gravitational lensing. However, these methods, they become quite get challenging at high redshift, where galaxies are quite faint and difficult to be detected directly. So this is where the main idea of this paper comes in. So instead of counting individual galaxies, the author use a method called as total light stacking. So in this approach, what they do is they take infrared images of many galaxy clusters, they align them, and then they stack them together. They say by doing so, they measure the combined light distribution from all the galaxies, including the faint ones, as well as you could also get the intercluster light. Here, more specifically, they use weighted mean stacks, which is centered on the cluster position. They say the key advantage of this method is so that they could capture all the sources of the light, which will be making it more powerful, or it will be more useful to study distant clusters where individual galaxies become hard to detect or resolve. So now, to describe the data that they have used a survey called as Mad Cows 2, which has a very large sample of over 83,000 galaxy cluster. And so to classify this cluster, uh, they divide it based on signal to noise ratio, uh, which they say it correlates with the cluster mass and the redshift. And to properly account for the uncertainties in the photometric redshift, they use adaptive redshift binnings while they choose their redshift bins. And here in this figure, this is the setup in which they categorize they select the clusters. The x-axis shows the redshift and y-axis the signal to noise ratio. Here each hexagon, these small ones, it represents a group of clusters which is color coded by the number of objects within the cluster. And the rectangle, this outline, it shows the main redshift bin, and these dashed lines, they show subdivisions within the signal to noise ratio. So this figure is essentially how they have sampled, which they will later use for stacking and analyze the stacked images. Then they say that within their image processing, each cluster, the author they take they extract image cutouts and they mask bright stars and foreground objects and subtract the background, and then these processed images are stacked together based on the weighted average red bin segregation that we saw above. And they also mentioned that to ensure robustness of their stacking, they repeat this process over 1,000 times using bootstrap resampling, and this allows them to estimate uncertainties within their measurement. Now I will move on to the result. Uh, so this figure, the figure 2, is the central figure to this paper. It contains these three panels. The left one, it shows the surface brightness profile. The x-axis is the radius from the cluster center, and y-axis is the surface brightness, which tells us how much light is observed at each radius. So here, each data point, it represents the average light at that distance, which is obtained from the stacked images. So the gray area, which represents the uncertainty. So as we can see here, the light decreases with radius. However, at certain points, say here, the decline becomes noticeably sharper. And they say this is where the splashback feature, it begins to appear. And to further confirm this exact radius, they also do a logarithmic slope of this light profile. And here you can see that to see how rapidly the light is decreasing. We can see a clear minimum in the curve in the logarithmic scale. Uh, and they say this directly corresponds to the boundary where the infalling material reaches the outermost radius. Then later they also show the distribution of this splashback radii from the bootstrap samples. And here they say that a narrow peak, it indicates that the most measurements, they agree, confirming that the detection of this radius is statistically robust. Which they further explain here, saying that at least 90% of this bootstrap realization should show a dip in the slope. That is why they will consider that that is the uh, flashback splashback radius. Then in their discussion, they also compare their results with previous studies, and here it is shown in figure 3. Here, the colored points corresponds to the data from their work, and the uncolored one is from the previous work. They show that their results, they agree well with the previous measurement, even though the previous measurement have used a different approach to get the total light. And they say that interestingly, some results show a dependence of the dependence of splashback radius on signal to noise at lower redshift, which they don't see in this work. That is, they say that the splashback radius is smaller in smaller signal to noise in previous work, but not in their work, suggesting this total light stacking could be less sensitive to biases. And later, they also check the effect of background subtraction uh, to check if there are any systematic uncertainties because of this background subtraction. And they show that in this figure, and they include like they do. If the background is underestimated, they say that it could also create an artificial dip, and then if it is overestimated, then the splashback radius could become weaker. So they mention that background subtraction is critical, and it could affect the uncertainty in their analysis. And finally, they also do explore how the stellar mass is distributed relative to this splashback radius. So in this figure, here the x-axis is the redshift, and the y-axis is the ratio of the stellar mass outside the splashback radius to how much of it is inside it. So this here each point it represents the average value for each redshift bit, and they say that this value, this ratio, it increases with redshift. Um, and they say that this could mean that the cluster at the earlier times have relatively more stellar mass in their outer region than to the closer redshift, meaning that the clusters could be more actively accreting material at higher redshift, which is consistent with the present cosmological model. And to conclude this paper, the authors have created a new method to detect this splashback radii using total light stacking, and they show that their results agree well with the previous study, and this method is also more less biased and more reliable for high redshift galaxy clusters. So yeah, this is the summary of
Oh,
Sorry.
very nice summary. I was wondering why they use Y's. Isn't it, doesn't it make sense to use JWST or some more, bigger telescope because you
Mm.
need to detect faint light?
True. I was wondering that too. But I think what the author was mentioning is this mad cow survey is extremely well studied for this splashback radius measurement. So I think they were trying to choose a similar survey which already has a good, uh, like a cluster catalog which supports their study. I guess that is the reason. I'm not exactly
But
sure.
then they have this Matka survey from dark energy camera, right?
Yeah,
Isn't
yeah,
it
yeah, yeah, yeah.
better to use dark energy camera for me, the telescope's data rather than wise? It's just what is it, 40 centimeter, right?
Mm, that is true. It's true. I don't know. I don't know why they used wise. Yeah.
I think so. If people use JWST data, you can do a better work than this, I think.
Mm, probably. Probably. But this paper was pretty interesting because the author of this paper came and spoke about her work in colloquium at NTHU, and she was mentioning that um, we can only do this kind of study in very nearby redshift, and like probably maybe because of the instrumentation effect. But I was also checking with her if there is a possibility that this concept could be also present in protoclusters, but but I'm not sure if there is a scientific meaning behind that, because protoclusters are not bounded gravitationally.
Sorry, I have a question.
Mm, yeah, that's yes.
So they detected the signal in stacked image, then
Mm,
in wideband, right? So then
mm.
what is a source of this wideband? Intra cluster, say, are they detecting individual galaxies or are they stars in cluster?
So, from what I understand, it is just galaxies within the cluster. So, the way they make this stacked images, they find a cluster and then they center the image onto the cluster core surrounding its cluster member, and then they take a reduced image of that, and then they co-add that image with lot of cluster images based on the signal to noise and also the redshift. As
So,
in, if the clusters are present within this bin, then they co-add all the clusters within this particular bin.
so that means the center of each cluster can be adjusted, right? They can adjust the position when.
Yes, they can adjust the position.
But then
Yes,
the positions of individual galaxies, they cannot handle, right? So
yes, they
therefore,
cannot. Yeah, that is true.
so therefore, for some case, this position empty, but for some cases there's a galaxy here, then they stop everything. Many.
Mm.
Oh.
That is
Then,
true.
then how do they stack? Say the galaxy cluster has a different mass, right? They
So they say that they only worry about the total light from a particular galaxy cluster, and say if that galaxy cluster they are present within this signal to noise ratio and within this redshift, then they would stack all of these cluster together because they have similar signal to noise ratio and also similar redshift. And they don't care about if each cluster has the same cluster number of galaxies or say less number of galaxies, but they have like
Oh,
a
really?
minimum number of galaxies a particular cluster should have. I think it is
Okay.
1.
But then the cluster has different cluster mass, and then
Yes,
also radius can be very different, right? So
yes.
I wonder, actually they are mixing all the different clusters, but then maybe
Mm,
trying to find a typical, maybe this radius splash bar.
true, true,
Okay.
true. But this is the only comment that they give based on the mass, that they assume that the signal to noise ratio kind of matches with the
But then, how do they define this signal to noise ratio?
I.
Say, I can imagine, say, for single galaxy, say,
Mhm.
depending on brightness, they can find the signal to noise ratio, right? But this is the
Mm,
signal to noise ratio for one cluster.
mm.
I wonder.
I'm not sure.
Okay. But there's a way to define signal to noise ratio for single galaxy.
Probably. Yeah. Mm, no, they only give the statistics of their S.
I see.
I think probably in their previous paper it has
Mm,
better explanation.
I see. Yeah. Yeah. In this way, I wonder if we can really directly compare these different redshifts. Say, higher redshifts, maybe they are using only massive clusters. Lowly, they include the less massive clusters. Then,
That is true.
if they stack all everything together, then maybe what they are looking at may be different at different redshifts.
Yeah.
I wonder. Well, anyway, I think it's good to know this. I didn't know these kind of things.
Mm.
Thank you.
That's a very good point. But then at higher redshift, you're probably looking at more massive clusters, which we expect the radius will be larger. But
Right.
still, we see that splash radius is going down.
Going down.
So if you correct for the mass, if you compare the same mass, that this splash radius at high G are even smaller. I
Even
think.
smaller. Oh, right. Oh, in that
Yeah,
sense, maybe conclusion doesn't change. Maybe.
Mm.
Yeah, but I think what Techa-san says makes more sense. It'd be much better paper if they
I see.
compare the same mass.
True.
Thank you, thank you.
Thank you, Tetsu-san.
Okay, thank you, Sherry. Is there any other questions or comments to Sherry? If no, we can decide on tomorrow's presenter. For tomorrow, we have Terry and Manukna, and we need one more volunteer. Okay, Darian, thank you. Okay, if there is no other questions or comments, we can close the meeting now.
So, sorry,
Thank you.
I'm at the conference tomorrow too. So I'm not sure if I can join, but if I have time, I will join online. Thursday too. Yes.
Thank you, Professor.
Me too.
Thank you, Professor.
Me
Thank you,
too.
thank you.
Yeah. Thank you. Thank you. So thank you for your attendance. We can close the meeting now. See you tomorrow. Goodbye.
See you.
Thank you.
Bye bye.
Goodbye.